All right, so we're going to learn power rule today. And before I teach you guys power rule, let me mention for the last week or so, we've been working on something called the definition of the derivative, which was a really long and kind of hard question. It involved a pretty messy limit and two different variables, x and h. And I said, the good thing about the definition of the derivative is it's basically like the derivative, period, meaning it always works. It can be used to find almost any derivative, but it does take a lot of work. So for the rest of the chapter, we're going to focus on shortcuts. And these are big shortcuts. This isn't like, hey, I'm going to take a little bit of work off. We're talking about taking a problem like this and turning it into this. In fact, today's shortcut, the power rule, is the biggest shortcut of all. You're going to really like this one. So first of all, here's a new notation I'm going to use a lot in the notes, and I want you guys to be aware of it. Whenever I say d over dx, and I'm not going to actually, when I say it in words, I'm not going to say over. I'm going to call that d dx. When I do that d dx notation and there's something inside the parentheses, that's telling you to take the derivative of that thing. Whatever is inside the parentheses, I'm asking you to take the derivative of that thing. Basically find f prime of x if it was a function, f of x. Now here's another word that you're going to see in the homework, and I don't want you to be confused by. The word differentiate means the same thing. So you're going to see some homework questions. It may be today, if not, it's coming up very soon, where the directions say differentiate. That means find the derivative of. It means the exact same thing. All right, so what we're focusing on for basically the rest of this chapter really is polynomials. So we're going to look at the derivative of some different polynomials today. And what I'm going to do for the notes is I'm going to start with degree 0, which means no x at all, just a constant function. I'm going to work my way up, and eventually we'll get to the power. So, first of all, when a graph is a line, this is another important concept here to be able to understand, because before we get to the power rule, when you have low powers of x, when you have a constant function or a linear function, it's kind of a trick more than a power rule. So what I want you guys to realize, well, first of all, let me remind you that when we're taking a derivative, what you're doing is you're finding the slope of a tangent line. So we took a look at a function maybe that looked like this. And I said, I want to find the derivative right here at this point, that red point. So you guys drew in the tangent line, and you found the slope of that line. Well, it's important to realize that when the graph actually is a line, like if I drew a second graph here that looked like this, and I said, find the tangent line is the line itself. If I give you a graph that's already a straight line, and I say, I want you to find the tangent line at this point right here, the tangent line actually is the line itself. And that's an important concept for the first two things I'm going to talk about today. So, what that means is the derivative of any constant is always 0. Because a constant function, the graph of a constant function is a horizontal line. So if I were to go over here to the side and say, I'm going to graph the line y equals 2. Well, the graph y equals 2 is a horizontal line at 2. Now, it doesn't matter where it is. It could be at 2 or 10 or negative 20. It's a horizontal line, and its slope is 0. Well, if I ask you to take the derivative of that function at any point, doesn't matter if I pick a point here or right on the axis or anywhere, the derivative is the slope of the line itself, and the slope is 0. So that's rule number 1. The derivative of any constant is 0. If I say, what's the derivative of 5? The answer is 0. If I say, what's the derivative of 100 million? The answer is 0. So to use our new notation that I just showed you on the last slide, d dx, the derivative of a constant, c, equals 0. And that's going to work for any constant. Doesn't matter if it's a big number, a small number, a positive, negative, anything. So let's move up one level to a linear function. Now the derivative of x equals 1. And in fact, if you look at that, if my equation was y equals x and I graphed it, the line y equals x is that perfect diagonal line right there. And again, same thing. I pick a point anywhere on that. If I ask you to draw the tangent line is the line itself. And the slope of that is 1. So the derivative of x is always 1. And there it is with our new notation. And I'm going to come back to that in a second. I'm going to come back to that later. But these are two, I mean, this is kind of power rule, but it's really like shortcut rules you want to remember that go along with the power rule. The power rule is really for anything other than power 0 or power 1. So remember those two. Derivative of a constant is always 0. Derivative of x is always 1. For the rest of them, oh, also let me add this. Yeah, a constant just gets multiplied on. So if I asked you to do the derivative of 5x, you would say, well, the derivative of x is 1, and 5 times 1 is 5. So another good way to think of it, the derivative of any x term, the x kind of disappears and leaves the constant. So if I ask you what's the derivative of 100x, the answer is 100. So these are the two shortcuts you want to remember, constant terms and linear functions. Now for the rest of them, here's the power rule. And it might look a little confusing when I throw x's and n's and n-1s out there. It's actually a very, very simple rule. If I want to take the derivative of x to the n power, so this is anything other than a constant term or x to the first. If I want to do derivative of x squared, or x to the 100th, or x to the 1/2 power, you can do fractions. X to the -7, you can do negatives, anything. What you do is you take whatever the exponent is, n, and you multiply by that. Then you subtract 1 from the exponent. And that's it, you're done in those two very easy steps. So in words, I said for any other power of x, if I want to take the derivative of x to the nth, two very, very simple steps. I multiply the function by the exponent, and then I lower the power by 1. So let's try a couple of these out. I think you're going to be surprised at how easy it is. So let's say I want to do the derivative of x to the 4th power. So what I'm going to do, I'm going to leave the x there for now, and I'm going to work around it. So two very, very simple steps. My exponent is 4, so I do this. I multiply my function by 4, and then I lower the exponent by 1. 4 minus 1 is 3. And that's it. That's the final answer. You're done. And in fact, here's another one right here. Let's say I'm going to do 3x to the 5th power. So I'm going to leave the x and work around it again. So the first thing I do, this time my exponent is 5, so I'm going to multiply by 5. Now this time I have a 3 there already. So I do 3 times 5 is 15. And then I lower the exponent by 1. 5 minus 1 is 4. And again, I'm done. It's that simple. So I told you guys at the beginning of the notes, you're going to like power rule. It's going to save us a ton of time over the definition of the derivative. This works for any power of x, whole number, positive, fraction, negative, doesn't matter. This will always work. All right, so let's take a look at this one right here, the derivative of 1 over x. Now the first thing I want to do, or the first thing I want to say, is that you cannot do the power rule separately. Like some people might look at this and say, oh, the derivative of 1 is 0, and the derivative of x is 1. So the answer is 0 over 1, which equals 0. It doesn't work that way. You're not allowed to do that when you have any multiplication or any division involved in the problem, division meaning fractions. And in fact, the next two sections of the book are called the product rule, which is when you have multiplication, and the quotient rule, which is how you could deal with something like this. Now, since we can't do it separately, sometimes, since we haven't learned quotient rule yet, you can kind of work around it. And the way I'm going to work around this is using properties of exponents. I'm going to say if I have 1 over x, another way of writing that is x to the negative 1 power. Now once you've done that, even though it's a negative exponent, that part doesn't matter. But once you've gotten a nice single x all by itself, now you can answer the question using product rule, or using power rule, sorry. So I'm going to leave the x, and I'm going to kind of work around it again. So I'm going to multiply by my exponent, which is negative 1, and then I'm going to lower the exponent by 1. Now negative 1 minus 1 gives me negative 2. So what I have is negative 1 x to the negative 2, and you could leave your answer like that, or what you can do is write it as negative 1 over x squared. You can change that negative exponent back into a positive. That would probably be your best answer there. So the derivative of 1 over x is negative 1 over x squared. I know I've done that question with you recently. It might have even been on the test we just took. But we did it using definition of the derivative, and it took a ton of work. You had to write out 1 over x plus h minus 1 over x and multiply and cancel and do this. There was a whole bunch of work to it. With the power rule, it's much, much easier. And I want to do one more similar example with you guys. Square root of x. Now again, we haven't really learned how to do square roots. We've only learned power rule. But you learned last year how radicals can be expressed as fraction exponents. So my step 1 for this question would be to change that square root to a 1/2 power. So remember, square roots can be written as a 1/2 power, and then I can do power rule again. So when I'm taking the derivative of x to the 1/2 power, I'm going to leave the x. I'm going to multiply by the exponent, which is 1/2. And then I'm going to lower the exponent by 1. Now you want to be a little bit careful with fractions. I'll do this work off to the side here. If I'm doing 1/2 minus 1, what I need is a common denominator, which would be 2 over 2. And 1/2 minus 2 over 2 is negative 1/2. So my exponent in my answer is going to be both negative and a fraction. And you're welcome to leave your answer like this. This is fine. You can always leave fraction and negative exponents, I don't mind. But if you wanted to write it back as a radical, what you would have to do is this. You would have to basically take the 1/2. The x to the 1/2 is going to go to the denominator because it was negative, and it was a 1/2, so it's also going to switch back to a square root. So that would be the other version of the answer. The derivative of the square root of x is 1 over 2 times the square root of x. Either one is fine. What I boxed up in yellow or green works perfectly fine. But you get the idea. That's power rule applied to, first we did whole numbers, that was easy. Then we did negative numbers, and now we did fractions. It works for all three. Now the next piece of the notes is, what if we have more than one term? What if we have a polynomial? And what I've done is I basically kind of copied this straight out of a textbook. This is a confusing looking notation. The derivative of f of x plus g of x equals the derivative of f of x plus the derivative of g of x. You look at it, that's a mess. That looks very, very confusing. Well, there's a much easier way to say that. What it says is, if you have separate terms added together, you can just do the derivative separately. And that's what this is saying. Instead of thinking of this as all one derivative, I can just take the derivative of this part, take the derivative of this part, and then whatever sign is between them. If it's a plus, leave it a plus. If it's a minus, leave it a minus. But whatever sign is between them just stays in between them. So this is just a way of a very complicated looking way of making actually a simple statement and saying that derivatives can be taken separately. So for this example, let's say I asked you guys to do the derivative of, and then we have a polynomial, 2x to the 4th minus 3x squared plus 1. So all we have to do, it's actually very, very simple. I'm going to do power rule on this one. I'm going to do power rule on this one. And then for this one, remember, it's not really power rule, so you always want to keep that in the back of your mind. Whenever you have a constant, the derivative is 0. And whenever you have a linear function, the x kind of disappears and leaves the constant. So those aren't really power rule. Those are separate rules you want to remember. But basically, this is 3 problems. I went ahead and typed this one out. This is, and I wouldn't show this work. If this were a homework question, I would not write d dx 3 times and split it up. This is just for the notes. But this is what I'm saying. Like the first one is the derivative of 2x to the 4th. And then the second one, I did a minus in the middle. And the second one is the derivative of 3x squared. And the last one is the derivative of 1. And for each one, remember what you're really doing here, you're taking the exponent, you're multiplying it times the constant, and then you're lowering it by 1. So my first one, 4 times 2 is 8. Exponent lowers to 3. 8x to the third. And then I copied that minus there. And then for the second one, I do the same thing. 2 times 3 is 6. Lower the exponent. 2 minus 1 is 1. And the last one, remember, you don't want to make a mistake there. That's the one where any constant, doesn't matter what the number is, if it doesn't have an x in it, the derivative is 0. So for my final answer, I would just say 8x cubed minus 6x. I don't need the 1 for the first power on the x. I don't need the plus 0 on the end. That basically disappears. So yeah, again, it's a nice, easy question. And really, honestly, I typed out a lot of stuff for the notes, but if this were an actual question, I don't need to see either of the 2 middle steps. You're basically going straight from here to here because it's very simple. You're going 2 times 4 is 8, so I get 8x cubed, minus 3 times 2 is 6, drop the exponent, I get 6x. The 1 just disappears because the derivative is 0, and you're going straight to the answer. So that's basically power rule. There is one more thing I want to mention to you. Oh, actually, there's one more example I wanted to do with you. So I can do this. Remember that one I did with you, 1 over x, where I said we have this really tricky looking question here. You look at this and you think, okay, I'm not allowed to do the top and bottom separately. Remember, I mentioned that earlier. That would be quotient rule. So I can't do power rule on the 2x to the 4 and the 3x squared and the 1. In fact, if you notice, that's the same polynomial we just did. I just put it all over x squared, or square root of x. So what we need to do is we need to manipulate this. We need to change it into something we can work with. So the first thing I would do is I would rewrite this. Let's leave the top for now. So that's 2x to the 4th minus 3x squared plus 1. And I'm going to rewrite this as x to the 1/2 power. Now, I still can't do the problem. It's still a fraction, but I wanted it to be all, like, basically if you're doing derivatives, you want to get into that habit. Anytime you see a square root, just rewrite it as a 1/2 power, so hopefully we can do power rule. But what I want to do is I want to do one more step. I'm going to do this. I'm going to take that x to the 1/2, which is in the denominator. I'm going to move it up to the top and make it a negative 1/2, because remember, that's what negative exponents do. They bump you from one side of a fraction to the other. So instead of this thing, 2x to the 4th minus 3x squared plus 1, instead of dividing by x to the 1/2, I'm going to think of it as multiplying by x to the negative 1/2. And then I'm going to distribute that. So what I'll have is, now here's where you want to be careful again because we're dealing with fractions. So I'm going to have 2x to the something power. Now I'm going to be real careful here. When you're multiplying x's, you're adding the exponents. So my exponent is going to be 4 plus negative 1/2. Now with a common denominator, that would be 8 over 2 minus 1 over 2, or 7 over 2. So your exponent on that first term is going to be 7/2. And then we're going to do that one more time. When I do the second distributive part here, we'll still have negative 3 for our constant. That's not changing. But for my exponent, I'm adding the exponents. This time it is x squared, so this time it's 2 plus negative 1/2, or you could do minus instead. That would be 4 over 2 minus 1 over 2. That's going to be 3/2. So your exponent for the middle part is 3/2. And then the last part is easy, at least for multiplying, because you're just multiplying. And there is no x there. So x to the negative 1/2 times 1 is, let's stay in red here, x to the negative 1/2. Now, that was a lot of work, and you're still not done with the question, because all we did was we got it to look like a polynomial. We got it to look like separate terms. Now we can actually do the power rule. So for the final answer to the question, I'm going to take each one and I'm going to multiply. 7/2 times 2 would be 7. And then you lower the exponent by 1. Now 7/2 minus 1 would be 7/2 minus 2/2. Our new exponent is going to be 5/2. Okay, same thing for the second piece. I multiply the exponent. 3/2 times 3, oh, it's minus also. 3/2 times 3 would be 9/2. And for our exponent, we have 3/2 minus 1, which would be 3/2 minus 2/2. That's going to be 1/2. So our exponent is going to be 1/2. And then for the last one, we are going to multiply by negative 1/2. And I'll try to squeeze it in here. Negative 1/2 minus 1, I don't really have room to write it out, but it ends up being negative 3/2. So I threw in that last example just to show you power rule can be a little bit tricky. It's not always just like, okay, multiply, subtract, done. You know, these questions, a lot of them are that easy. A lot of them you're done in 10 seconds. But you can have a question that's a little bit tricky, so you want to be careful with those, especially when you're dealing with properties of radicals, like we did here, and especially when you start dealing with fraction and or negative exponents. All right, one more thing. I know this was a long day of notes again. So remember in the last section, we did that question where we were finding the slope or possibly the whole equation of a tangent line. And back then I said, okay, 90% of this question is doing the derivative, because that's when we were doing definition of the derivative and it took a ton of time. Now all of a sudden I can ask you that question and we can do derivatives using power rule, and that part's a snap. That part's done in 10 seconds, and then the question becomes much easier. So let's do this question right here. We're going to find the equation of the tangent line. We have our function f of x, and we have an x value, x equals 2. Now, the way we started this question last time is the same way we're going to start it this time, by finding f prime of x. But we're not going to do definition of the derivative anymore. In fact, I'm going to say from now on, unless the directions specifically say, use the definition of the derivative, don't. Our goal is to avoid that. That's the most work. So what I'm going to do instead is I'm going to do power rule. And it's nice, easy whole numbers too. So I go 2 times 2 is 4. Lower the exponent to 1, you get 4x to the first power, or 4x. Now for our other two, it's not really even power rule, it's a shortcut. So the derivative of negative 3x is just negative 3. Remember, when you have an x by itself and you take the derivative, the x part just disappears and leaves the constant. And the derivative of 7 is 0, so that's literally going to disappear. And I'm done. So that work that would have taken, you know, if I had done this question using definition of the derivative, I would have had to fill up this whole slide, probably click to a new slide, fill up that whole slide, just to find the derivative. We did it in 10 seconds. 4x minus 3. Now let's finish out the tangent line part. So the next thing we want to find is the slope. And to find the slope, we plug this number into the derivative, f prime of 2. So that would be 4 times 2 minus 3. 8 minus 3 is 5. So the slope, m, is 5. Now the only other thing we need is a point on the line. And our point is x comma y. And we already know the x value is 2. All we need is the y value. Because remember, I told you x was 2 in the question. So this is one of those where you're going to go back to the original problem. Oops, not f prime. Let me erase that so we're not confused. Yeah, it's not f prime anymore. We're doing the original function and just finding f of 2. So that's 2 times 2 squared minus 3 times 2 plus 7. I just plugged into the original function. 4 times 2 is 8, minus 6 plus 7, so that would be 2, let's see, that would be 9. So my point is 2 comma 9, and then we will finish the problem with our slope formula. Y minus y1 equals m times x minus x1, point slope formula. This is my x1, y1. We already had m up here. We got everything we need. So my final answer is y minus 9 equals 5 times x minus 2. And we're done. And the point of that was like, yeah, we've done all that work before. The point of that was realizing how quickly we can now do this. Doing the derivative is a snap now if it's power rule. So again, I don't want you to do definition of the derivative anymore unless you are specifically asked to. From now on, we're trying to find derivatives the fast way.